Okay, so just one more video on theory for our trees before we get into some actual programming. So we saw the idea of a tree, right? So we saw this idea of a tree, which is a graph that is connected, it has no circuits, and it's undirected. And then I introduced to you the idea of a binary tree, which is a tree where each parent node has at most two children. It could have one child, zero children, or it could have two children, and those were the only options available. I'm now going to introduce to you the actual data structure that we're talking about in this section, which is a binary search tree. A binary search tree is a tree, and it's a binary tree, as the name implies, which means that each parent has at most two children. But there's an important property about our binary search tree, and that is that everything on the left-hand side of a node has a smaller value than it, and everything on the right-hand side of a node has a larger value than it. So let me give you an example of this by taking a look at maybe a list that we may represent in a binary search tree. So let's suppose that we have the following values. We have the values 50, 30, 70, and we'll say 20, 40, and we'll say 60, 80. Okay. If I were to say that 50 was my root node, the next question that you may have is, where does the value 30 go? Well, if we take a look at this root, I said that everything to the left of it needs to be a smaller value than it, right? So that means that 30 must be on the left-hand side of 50. So I'll place it right here on the left-hand side. Now 70 is the next value that we have. Where would 70 go for this? Well, I said everything to the right-hand side of a node is bigger than it. So since 70 is bigger than 50, it must go over to the right-hand side here, right? Now, what if we wanted to place 20 in? Well, 20 is smaller than 50, so we come down here and we say, well, is 20 smaller or bigger than 30? It's smaller than 30, so it must go to the left of it. Additionally, 40 is smaller than 50, but it's bigger than 30, which means that it goes to the right of 30. 60 is bigger than 50, but smaller than 70, so it goes to the left-hand side. 80 is bigger than 50, and it's bigger than 70, which means that it goes to the right-hand side. And there we have a binary search tree. Everything to the left of a node is smaller than it. Everything to the right of a node is bigger than it. If you pick any parent here, say 70, its left-hand side is always smaller than it. Its right-hand side is always bigger than it. So why is this useful? There's a few important properties of this tree that are going to be very beneficial to us. The first thing that I'll point out to you is that the rightmost node, so the one that's the furthest to the right, is always the biggest value in the tree. Similarly, the one on the left-hand side, the leftmost node, is the smallest value in the tree. So it's pretty easy to find the biggest and smallest values using this kind of tree. The second thing that's really helpful about this tree is that it's very fast to search. Suppose that you wanted to find the value 20 inside of this tree. The way you would do that is you would start at 50, and you would say, is it bigger or smaller than 50? In this case, 20 is smaller than 50, so you would go to the left-hand side. But do you see what happens when you do that is that you remove this whole branch from being possible. You just excluded 3 values from the search. So in one single comparison, you were able to eliminate really 4 possible values, including the 50, from your actual search. So you essentially reduced the amount of space you need to search in half. And every single time that you do this, you actually do that exact operation. So now there's 3 values left. When we take a look at 30, we say, well, it's less than 30, so we move to the left. We effectively eliminate half of the search space, and we arrive at our value. And you see that it actually only took us 2 operations to get to the value that we were searching for. If we were doing this in a linear search in this original list here, we would have had to do 1, 2, 3, 4 operations. So we did twice as many operations. And that was really a pretty decent case because it was in the middle of the list, right? If it were at the end of the list, this would have taken O of n operations to complete. It turns out that with the binary search tree, because of the fact that we eliminate half the tree every time, it actually takes log of n operations to search through it. So it's significantly faster than our linear search. So those are the main examples of our binary, the main use cases of our binary search tree. It makes searching extremely fast. So if we need to store data in a way that we need to be able to search it pretty quickly, we've seen a few different approaches for this, but the binary search tree is one that allows us to do it in a very easy way, and also allows us to do it in a pretty, memory constrained way and fairly quick way overall. So this gives you the idea of how the binary search tree works. At this point, hopefully you've seen enough intuition now that it's going to be pretty clear how we're implementing this tree and how our implementations are generally going to work. So thanks so much for watching, and I'll see you in the next video.